Hi everyone, and welcome to this tutorial on RSPt calculations. And in this video I will show you how to put certain electrons into core. RSPt is a full potential code which gives you a lot of flexibility how you can treat your electrons. You can either assume that they belong to non-interacting core, so they just belong to their atom, or you allow the states to fully hybridize and then you treat them as valence. This is a schematic picture showing the typical electronic structure of transition metal. So we have valence electrons formed by 3d, 4s, and 4p states of transition metal, for example iron or cobalt. They are dispersed states and we form beautiful density of states around Fermi level. Few tens of electrons below Fermi level, we also have 3p and 3s states. They are called semi-core because they don't lie at energies deep enough to be associated with core, strictly speaking, but nor they contribute to the chemical bonding. So for certain properties, it's quite safe to assume that 3p states are just atomic-like. By default, these valence electrons belong to one energy set, and deep lying 3s and 3p states, they belong to the second energy set. In this tutorial I will show you how to instead treat these 3p and 3s electrons as core, assuming that they don't interact with the environment and they can be treated as purely atomic. So in practice, what we're going to do, we would like to remove 3s and 3p electrons from the valence and put them in a core. It means that these states are not anymore part of our basis, which means that we will have to modify the element file. If there are no more semi-core states in the calculation, we can completely get rid of energy set 2, so we will have only one energy set. And finally, we need to take care of the number of valence electrons, which we explicitly specify in the header file. Let's just go through the steps one by one. So let's go to the terminal. And again, we work with cobalt to iron aluminum. So first we go to element file of iron. This is the list of core states: 1s, 2s, 2p states, and that's it, because 3s and 3p states are treated currently as valence. So let's change this. Now we say that the 3s and 3p states are completely filled. Since we removed these electrons from the valence, we don't need to specify them here. They are not part of our basis anymore. So we can safely remove these 4 states. And also, we will get rid of the energy set 2 completely. So we can also remove these 4 lines. Now, since these states don't have any states to be orthogonalized against, we just restore their linearization energy flags to the default, which is 0. Like so and like so. Okay, and here we removed 4 states, so we just have 8 types of basis functions. Now we do the same for cobalt. Again, we populate 3s and 3p states. We remove those, changing linearization energy flags to the default. Remove those, and done. What else? We need to change the panel data, which currently states that we have 2 energy sets. Instead, we're gonna have only one. Did I forget anything? Yes, I also need to modify the element fire of aluminum, because for the moment it assumes that there are two energy sets, although it was redundant for aluminum from the beginning. So we just remove these 4 lines from the bottom. But otherwise that's it. What else? I now have to go to the header and make sure that I have the right number of valence electrons. We used to have 53 valence electrons, but we placed 3s and 3p states of both iron and cobalt into the core. So how many electrons is that? Which we have to subtract from the valence. So 53 minus 24 is equal to 29. You can see we indeed decreased the number of valence electrons quite significantly. So that will definitely make our calculation faster. At this stage, I think we can just regenerate the data file. So let me start from scratch. And let me run one RSPt iteration. That was fast. The iteration was successful. We start the calculation from scratch, so FSQ is quite high. The magnetic moments are reasonable, and the total moment is close to 5 Bohr magnetron. That's what we used to have. So what changed? Here are the calculated core states for each element in our unit cell. So this is cobalt. Now we have this 3s and 3p states. This is their energies. And since the wave functions of these orbitals are a little more extended compared to the rest core states, they can leak out from the core radius. And the integrated charge of electrons which are leaking out from the core sphere is shown here. So it's 0.016 for cobalt and 0.026 for iron, which sounds like a big number, right? But if we scroll down, we can see that the core electrons of aluminum give a comparable leakage. So these values don't look that large anymore. So what we can do now is converge this calculation down to some decent value. Okay, it looks like it converged. Let's look at the bottom of the hist file. Yeah, we reached very low value of FSQ. We got a magnetic moment of 4.93 Bohr magnetron, and this is the total energy. I think the calculation looks good. What we can do now is to compare what has actually changed as compared to the calculation where we had 3s and 3p states explicitly in the valence. So I run vimdiff between this out file and the out file of our previous calculation. You see that magnetic moments are almost unchanged. If you look at the total energy, that changed quite a bit. So watch out when you compare different calculations where you have these semi-core states as a part of your core or valence. One a little special situation is when the core electrons have to be treated as spin polarized. And the classical situation is the case of magnetic lanthanides, such as gadolinium, terbium, thulium, etc. Here is a schematic picture of the electronic structure of these systems. We have valence electrons, which are composed of 6s, 6p, and 5d electrons. They form quite dispersed states, which are spin polarized. However, the largest part of spin polarization is carried by 4f electrons, which are extremely localized, but they have to be treated as magnetic. So, we don't only have to place them in core, we also have to make sure that they are polarized, meaning that spin is assumed to be a good quantum number, therefore we have to neglect spin-orbit coupling. I have prepared a separate example of gadolinium, which is a classical example of ferromagnetic lanthanide. To have a look at the crystal structure, we can look at the SIMT-INP file. Here it is. You can see it has HCP structure with 2 atoms in the unit cell, which are in fact equivalent. In order to make 4f electrons spin polarized, we modified the data file in the atom directory. Here is how it looks like. We have a lot of states, and here we have 4f states. And you see, we treat them in a scalar relativistic way. We have 7 electrons in spin up channel, and spin down channel is completely empty. And in the element file, we also did certain modifications. We added 4f electrons in the core. So here we are, 4f, and there are 7 of them. And in order to make them spin polarized, we set this flag to 1. And that's the only difference it makes. Now it will treat the 7 electrons as spin polarized. So it will put them all in spin up channel according to the first Hund's rule. And as you can see here at the bottom, this place was reserved for 4f states, but now we don't have 4f states, and instead we pretend that there are 5f states. So after you run the self-consistent calculation, you can have a look at the out file. And if we go to the bottom, we can look at the magnetic moment. And it's 7.62 Bohr magneton. 7 Bohr magneton come from 4f states, and only 0.62 is what comes from the RSPt states in the valence. If you look at the core states, now you can see that 4f states are treated in a separate way, because now they have a clear character of majority and minority, which stands for spin up and spin down. And this is their energies. One is located at 0.04 Rydberg, and another one is at 0.41. So that's it for today. See you next time, and until then, enjoy RSPt.